What's up? How are y'all doing? Good. All right. So I was able to get. Obviously, I'm here to start maybe like the first day of biochem tutoring. Is everyone here interested in being here for this?
Yes.
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 Cool. All right. If I could have actually most all of y'all kind of come up closer, just because I kind of like being engaging. Hopefully that's not too much of a hassle. If it is,
What if I'm loud?
well, that means I'll hear you very well. So that's awesome.
What if we're charging?
There should be outlets all up along these aisles.
This road. Yeah.
So as I said earlier in class when I came in, my name is Andrew Oestreich. I'm going to be the large group tutor for biochem, both 1 and 2. A little bit about myself. From UT, I'm a UT grad if you couldn't tell by my shirt. Had a major in exercise science, and I took all the major science classes that biology, chemistry major classes people had to take. Had some difficulties with some, had some successes in others, but actually didn't even take biochemistry until I got here. I took organic chemistry because that was one of the prereqs that Parker makes you take. And I'm still trying to figure out where that prereq comes into play, but whatever, it's fine. But I've got a large chemistry background. I really like the chemistry aspect. The biology aspect is kind of the learn to love. So hopefully y'all can learn to love everything with me as I have. So a lot of things that I'm going to be doing, going over some of the structures or how I teach is going to be kind of that chemistry background to have you draw things out, to kind of know the structure of it so that you can have that visual as opposed to just memorizing. Memorizing doesn't give you anything unless you can be able to apply it and remember it later for boards. Boards for y'all are going to be, y'all aren't even on the radar for that yet, but you know it's going to be a year and a half from now, and if you just straight memorize mnemonics or what have you, it's not the most helpful. So I'm going to try to give you some tools to have long-lasting memories for stuff. Yes?
You haven't had chemistry since like 2006.
If you haven't had chemistry, that's okay.
Or any other type of chemistry ever.
That's okay. That's what.
We get lost because even as much as he dumbed it down, it's still a mile over our head.
Yeah, that's okay. So I mean, so something that I remember when I was in undergrad, and the teacher would always be like, "There's no stupid question," and I'd be like, "Yeah, there is. There's like definitely a stupid question." But like as being a tutor, there really is not. People come from all different areas of knowing, probably haven't had chemistry since 2006. Maybe some before then, maybe some after that, whatever. Some may have never had it. So I welcome all questions. And really what I'm going to be doing is just kind of going lecture style, similar to Dr. Sarkar. Just kind of going each page by page, going over the exact same things he does, but maybe kind of presenting it in a different way so that it might resonate with you more, just to kind of give you that opportunity to hear it a second time and then remember it better, and hopefully better. Hopefully not worse. Probably not worse. So, but first, do y'all have any questions? I've kind of been trying to read what you're looking forward to or what you're kind of not looking forward to. Responses. I've had more not looking forwards to than looking forwards to. Do y'all have any questions for me about the course in general? Anything?
Quick question. All the tutors, how are y'all able to do this with all your first try stuff and come back and tutor? Honestly, like.
We really want to. Seriously though, we actually really want to. So I started off tutoring with the DAA Open Lab, which you'll be hearing from Courtney about. And Dr. G is amazing, if y'all already know that. And just being able to go to lab with him and see the excitement that he had about just a freaking bone, and he could just make it come to life, really, it just made me want to keep doing that and try to inspire that kind of learning my own to the next try ones and what have you. So that's kind of how I got into with that, and then talking with Dr. Sarkar, and just seeing biochemistry and how much I was kind of teaching my classmates how to do it, and I was like, oh well, if I'm teaching my classmates and they're doing pretty well, then maybe I should probably get paid to teach other classmates. So that's kind of what it comes down to, is if you found success in something that you really like to do and you want other people to have that same success, that's kind of where we're all coming from as tutors. So who knows, how far have y'all gotten in y'all's lecture thus far?
To the ordinary, tertiary, secondary, and primary structures.
And that's chapter, y'all are in chapter 3 already. Perfect. And y'all's test is when?
We had our first quiz today.
First,
Probably October 6th.
so like 3 weeks?
Yeah.
Okay, cool. Well, for those of you who did not fill out my survey, that's fine. I understand. Just that little questionnaire thing I had emailed y'all. Don't worry about it. It's not a big deal. I was going to tell you not to worry about it. So what I'd like to do is to have just a 2-hour session each week, kind of going over what hopefully that y'all have done this week. We're just doing a chapter each week, maybe more, hopefully not less. And then trying to stay on track with his schedule. That way we can just kind of be like a review of the previous weeks or of that week's. It's actually kind of a tie between Tuesdays and Thursdays where it's at right now, but I'll send you that information when we get there, just kind of focusing on today. But yes.
If you do set up a later time, like I had practice during then, can we set up an individual time?
Yes, so I haven't figured out, we have a new person who's in charge of coordinating all the tutors, and she's still trying to figure out how to get y'all to sign up for individual times. And so I'm sure here by the middle of next week, all those individual times should, in theory, be posted for when people are available. It may not be with me specifically, but there may be other tutors that you can sign up with, absolutely. So if the one-on-one tutoring is something that you really want to do, there will be one-on-one tutors. Cool. So any more questions? Y'all want to hear about me anymore? No, you don't? Okay, good. All right.
What try are you on this
Try 4. Did not say it. So yeah, I'm going to try 4. There's really not a lot. Y'all will learn how, it's fun. Try 4 is actually really cool. We learn about neuro, but we'll learn about biochemistry now. So, all right. If you don't have this book, that's what mainly, I'm just going to Sarkar style it. Like he just has it all on slides already, but I'm just going to go kind of page by page with what's in here. From my experience with Dr. Sarkar, pretty much all the test questions do come out of this book. If you don't have it, there's probably someone trying to sell or rent it on the Parker Classifieds page. Or you can just copy down everything that's on here in your own handwritten notes. So this is the first time I've used this contraption, so I'm going to try to zoom it in. We'll see if that works. Hell yeah. Cool. And I do like the sound of my own voice, but I really like y'all's voices better because being engaging, there's the different types of learning y'all learned with Dr. Elbel, the kinesthetic or what have you. So if there's something that you would like me to do that will help you out more, or something that you don't like me doing, please let me know, because this is all for y'all's benefit, and I don't know what works best for you unless you tell me. So please, talk. All right, chapter 1 is a review of basic chemistry concept. So this is really just going to get down into what you probably last heard in 2006, or what was your name? Jared. And actually, so if I call on you, it's kind of hard when you're pointing, but please say your name. It'd be kind of cool if we kind of know each other. That'll help y'all learn each other's names as well. Jared. Cool. So biochemistry, what the hell is it? It is the chemistry of life. So pretty much everything that is going on in our bodies, in our pets' bodies, what have you, can really be defined by biochemistry and all the biomolecules and interactions that are going on within them. So coming here, we have our cell. So this is just kind of that basic freshman year of high school biology review. So we have the different parts of the cell. We've got the nucleus, obviously, where the DNA is stored. Do you all want me to go over this? Do you all want me to like go through each of these organelles, or do you all want me to skip over that?
Gonna be tested over?
I mean, he'll probably ask you what a mitochondria does, and you're going to say what? The powerhouse of the cell, right? You know, like, yeah, exactly. So really, I mean, we know what the nucleus does. We know ribosomes make the proteins. And the mitochondria, talking about the mitochondria, we've all heard the powerhouse of the cell, powerhouse of the cell. When I wrote that definition down in high school, I was like, what the? I don't know what that means. I still don't know what that means. So it's actually where we make energy at. That's what it means by powerhouse of the cell. That's where energy is created. And so ATP, absolutely. We have our smooth endoplasmic reticulum. I don't know why they named it that way. It was really stupid, but whatever. Our SER, so that's the site of where that's where lipids are made and drugs are metabolized. So alcoholics. So why do we just learned this in try 3? Why do alcoholics have a higher tolerance for alcohol? Right, it takes more to get them drunk than it does me my freshman year of college.
They just have a denser SCR.
Yeah, they have. So they have more smooth endoplasmic reticulum. They have more proteins in there to actually like kind of to break down that alcohol faster, and so that's why they're able to drink more, and so they can't get drunk as fast. Fun fact of the day: take it home to your parents. No, don't do that. Lysozymes, they're in charge of degrading intracellular debris. So they're kind of the trash keepers, the trash men in the cell. They're if they see something that doesn't need to be there, any waste, they're in charge of making sure they're grabbing that and breaking that down and taking it out of the cell because we don't need it, right? We don't want waste in our body. Our Golgi complex, it packages, targets proteins to other organelles for export. So let's just go through the process of how a protein's made. Okay, so DNA is transcribed. So DNA starts in the nucleus. All right, so then it gets copied, right, and then it becomes an RNA. It gets transcribed into an RNA. It leaves the nucleus as that RNA, messenger RNA, and then it's going to be translated into a protein. So understanding the difference between transcription and translation. So transcription is when it goes from DNA to RNA. Translation is when it goes from RNA into a protein. And we'll get to that actual physical process first.
Can you say that one more time?
Yeah. Transcription is going from DNA to RNA. So it's taking that stored information and putting it into kind of like a medium to where it can be used later. So kind of changing it from one language to a different language that's more accessible. And then the RNA is taken to the ribosome, and it's translated into a protein. So that's where, so translation is taking an RNA and making a polypeptide or a protein. See, what else do we have on here? Like we said, ribosomes, protein synthesizing machines. Our cytoskeleton supports the cell and aids in movement of organelles. So cytoskeleton, like what does our skeleton do? It supports our body. It allows us to have attachments for our muscles and to be able to move as levers. It helps us be upright. So same as thing, the cytoskeleton, cyto meaning cell, skeleton, keeps it upright. Rough endoplasmic reticulum is a site of protein synthesis. So differentiating between the rough ER, that's just easier to say ER because I can't say the other one, and the smooth ER is ribosomes. So when you get into micro lab and you're looking under the microscope and you're looking at the rough ER, you're going to see all these little black dots on it. It has that like roughened, peppery looking thing, like it's been seasoned. So those are the ribosomes, those same things that are making the proteins that I just talked about earlier. So that's the difference between the rough ER, which makes proteins, versus the smooth ER, which makes fats. So that's that difference between the ribosome presence either there or not there. And you have transport vessels. He's not going to ask you about anything about that. But there's things that take things to and from within the cell. And coming back to the Golgi complex. So proteins are made by the ribosomes that are on the rough ER. And then what the Golgi does is it takes those proteins that were made and it packages it. And it's kind of like the UPS truck and tells you where it needs to go. It makes those like final, puts it in the box, and it makes the shipment to wherever it needs to go in the cell, whether that be over here, whatever it's meant to do. That's what the Golgi does. It packages it and ships it to where it needs to be. So that's kind of a general cell. Lots going on, right? Lots going on, which is really cool because that gives me a lot to talk about, and y'all have a lot to learn about. Any questions on that? Did I go too fast? Is that a decent enough pace? Yes. Yes. Cool. So, scooching up. And I've requested that this be vodcasted, so hopefully it's recorded. So I'm not going to curse too often, maybe just a little. But I don't know where it'll be yet, but I'm going to find that out, even if it was vodcasted, and I'll make sure that y'all know where you can access it.
Is this going to be the same time every week?
It's either going to be today at 5 o'clock or Tuesdays at 5 o'clock. It's been a pretty close race. Probably just flip a coin, see what happens. Do y'all have a preference? I mean, do y'all have a preference, Tuesday or Thursday?
Don't we have DAA on Thursdays too? I thought we had DAA on. Wait, what? But the DAA tutoring was Monday and Thursdays at 5.
There's 2 open labs?
Isn't it on the board?
I just talked with Courtney, who's the head person. She hadn't finalized like when the open lab would be yet. And I think she was looking at Mondays, but there might be a second one on Thursday. I was kind of personally thinking Tuesday just in case we did have a Friday off and y'all wanted to do something on that Thursday and just skedaddle. No one wants to be stuck here. Cool. Cool. All right, so just continuing down the page, characteristics of life, very complex. We have a lot of biochemical reactions. We have a lot of just things going on in our body right now that we're not even aware of. We're fighting gravity. We're making sure that oxygen is being taken from our lungs and put to the rest of our bodies, making sure our pH is in check within our body because a lot of things happen at once. So it's very complex. So our body needs to be able to sense the changes that it needs to be able to respond to what's happening, right? So we need to be able to determine what's good. I need to keep doing what's good, or if there's something harmful to me, like a lion about to attack me, I should probably figure out a way to run the heck away. So it's got to be able to respond to things both inside and outside of the body, and it's well adapted to do that. So chemistry. Let's learn about chemistry first. Elements, atoms, and molecules. So periodic table. Don't really worry about it. Just so like y'all see it, it's not really that big of a deal in this class. Just kind of this is just a basic background. But atoms. Atoms are the smallest unit in an element. So have y'all seen that? No, that's not a commercial, so y'all wouldn't have seen it anyway. It's a primarily composed of electrons, protons, and neutrons. All right, so does anyone have that kind of Bohr model in their head when they think of an atom, where you have like the nucleus is with the protons and neutrons, with the electrons floating around them, right? I'll draw it here. I brought a bunch of scratch paper. One of our neuro professor, he will draw something, and he'll just go like that, and he's like, "Yeah, draw that," and I'm like, "No, thank you." So I'll try to draw better than him. So we have. This is just the atom. So we have kind of a cluster of protons and neutrons. I'm just going to put a plus for protons, whatever. And then around it are these electrons, right? That electron shell flying around. So protons, neutrons. Protons have a positive charge on them. Neutrons have a neutral charge on them. And electrons, just kind of process elimination, have that negative charge on them. So in a lot of the chemical reactions, we're going to be dealing with the exchange of electrons. So in about a month or so, we're going to be talking about the electron transport chain. So it's basically stripping electrons off of atoms and then taking them somewhere else and putting them on different places or using them in different ways to be able to make energy or produce energy or to use energy or to store energy. So a lot of the energy that is held in our body is really just in where these electrons are at in a bunch of different atoms. I don't know, I think that's cool. You know, maybe y'all don't, whatever. So electrons, protons, neutrons. So the protons and neutrons are in the middle with the electrons circling around them. So then we have molecules, and they can be inorganic, organic. Organic, I think, is your carbon, nitrogen, oxygen, phosphorus, sulfur, chloride. Inorganic are the ones that are not those. He's not going to test you on that. I'm going to be pretty upfront of telling you, like, if something's like test-worthy or something's really not test-worthy. That makes it a little bit more. Y'all like perk your ears up, like, oh look, there's a test question. Cool. All right. So, and like here's that picture that I probably should have just shown you this instead of drawing it crappily. So the nucleus, protons, neutrons with electrons kind of going around it. All right. So electron shells. Kind of hinted at it earlier, but so electron shells or orbitals are in layers around the nucleus. So it's kind of like an onion. They just kind of go out with each little layer. The number of shells depends on the atomic number. So going back to, I'm just going to reference the periodic table just to kind of show you. You will never have to like label anything on the periodic table or like memorize that information at all. So this is just all reference here for you. So we have different rows, right? Rows go across, right? Columns go up and down. Cool. Yes, and any verbal yeses? I got head nods. I'm pretty happy. Cool. So we have one row across with hydrogen through helium, one row across from lithium to Ne, whatever the heck that is. Neon. There we go. We got some science people. Sodium to argon, whatever. So that's row 1, 2, 3, and so on. So hydrogen and helium only have one valence shell. They're in the first row. They have one shell. The next one, lithium, is in that second row. So it has two valence shells. So it's just adding another layer onto it. Sodium, 3 valence shells. So it just builds like that. That's how you know how many valence shells you have. And so staying on this page, no, going back to this one over here. So the first shell can contain only 2 electrons. All right, and so that's just, these are kind of the rules for the valence shells. This is something that he will test you over. So just understanding it, man, it's actually difficult to keep up. Let's just do this. I'll slow it down. So the first shell can only hold 2 electrons. All right, and that's because, going back to that periodic table, there was only hydrogen and helium in that first row. There were only those 2 elements. So that's all you need in that first shell because there's only those 2. One for, basically one for each. So hydrogen would have 1 electron, and helium would have 2. And I'll go and explain that here just in a second. But the second shell has up to 8 electrons in it. And that is because if you look and you go across and you count 1, 2, 3, 4, 5, 6, 7, 8, there's 8 elements going across in that row. So that's why there's 8 in that shell. Same with row 3. There's going to be 8 in that third shell as well. So if he's ever trying to ask you how many electrons are in the first valence shell, just think the periodic table. There's only 2 elements in that first one, so there can only really be 2 electrons, or in the second shell, or then each successive shell will have 8, and that stays true for here because these are all weird. If y'all remember, there's all like scrunched up, but each successive shell will have 8 electrons in it max. Does that make sense? Questions, comments, concerns, compliments? No?
Doing great.
Okay. Cool. Cool. All right. So as we increase the number of shells, we're going to get higher and higher energy. And you're going to think, why is that? Oh my God, this is so frustrating. Let's see what happens if I do this. Hell yeah. Hell yeah. All right. So as we increase the number of shells, it's higher and higher energy. So what's keeping the electrons in the shell is that the difference in charge between the positive, the protons in the nucleus, and the negative electrons. In chemistry, opposites attract. So the positive and the negative want to come together. So that's what's keeping all these electrons in that shell, is that they're drawn towards that nucleus, right? And so as we add on layers to that onion, and those electrons get farther away, it takes more energy to keep them in, right? Because they're farther away from that positive charge, so it takes more energy to make sure that they're close. So that's why as we go out in the distant shells, they have that higher energy. Valence electrons are those in the outermost shell. Test question, test question. It's underlined even for you. So what that means is whatever, so say, I guess we're going over to the next page, page 5. We can see that sodium has 3 shells, right? The first one has 2, is full. The second one has 8, also full. This third one is the outermost shell, so that would be the valence. So there's 1 valence electron in that sodium's out in their valence shell. I'll keep saying the word valence, so maybe it'll get drilled into you. But really, that's the ones that we're using for all these reactions, right? So going back, I got to figure out how I'm going to like walk back and forth between this thing. So if we're here, these are on the outside, right? So that's the ones that are most easily used. Try like an example, like when you're going shopping and you're picking something off the shelf, right? You don't like part things and like reach the one in the back, right? No, you want the one that's right in front of you to get and put in your cart. That's the same. That's the same with this. That's the same with this. So like in this example here, like this outer shell would be the valence shell, and these are the electrons that we can use in those reactions that another molecule can take, or this can give to, or vice versa, just because it's the most readily available. It's the easiest to take and to give off. So that's really all what the valence shell means. It's the one that's active, the one that's participating in all the reactions. So a rule with valence shells is they like to be in balance, or they like to be kind of in an equilibrium state. So what does that mean? So they either like to be full or they like to be empty. So let's see. Yeah, so going over to this example here, we'll talk about the definitions that are around it. But so you can see that in sodium, the first shell has those 2, so it's full, right? Because it can have a max of 2 in its first shell. The second shell has 1, 2, 3, 4, 5, 6, 7, 8, right? So it's max. So then it goes to this last shell, and it only has 1. And it's going, hey, I only have 1 when I can have a maximum of 8. It's not really a high percentage of being full, is it? So there's really 2 things it could do. It could either you can either add 7 more to make it have its full 8, but that would take a lot more than to just dump that one and then just be full here, right? So that's what sodium's doing here in this example with chlorine, is sodium saying, hey, like I only have this one shell, and it's kind of making me itchy. Like, I really don't want it. I don't feel right. Well, chlorine over here on the other side of the periodic table, it's got these two full, but this last one only has 7. It's missing that 1, right? So it's like, hey, I need that 1 to give me that perfect 8, so I'll take that off your hands, and then you can, you can have your valence shell empty, which kind of makes that one go away, right? And so they're both happy. So yeah, sorry, does that make sense? That make sense? Okay. So that's why we have sodium typically has a positive charge on it, because it's lost an electron. It's lost a negative charge, right? Electrons are negatively charged. So if it loses that negative charge, it's going to have more of a positive charge because it didn't lose any of these protons in the middle. So that's why it's sodium with a little positive on it. And then chlorine, going over here, it just gained an electron. It just added a negative charge. So that's whenever we see chloride, we usually see a Cl minus because it has that negative charge, giving it more electrons in its valence shell or in its total electron shells than it has protons. So that's where so whenever you see negatives and positives, that's really just talking about if it's a positive charge, you're missing electrons, right? Because you're losing that negative. And then if you're have a negative charge, which it's actually that one down there, probably pointing to these. If you have a negative charge, it's because you've gained an electron so that you're more negative now. That concept of gaining something but becoming negative is kind of hard for some people to understand. But just take some time with it. Question, what's your name?
Maddie.
Maddie.
I was just gonna say one thing, because I mean that's kind of like high school science. One thing that helped me with that, this is really stupid, but like when you gain weight, it's a negative thing for you.
Good one.
And then if you lose weight, it's a positive factor for yourself.
Good one.
That helps. That's the way I remember it.
Thanks, Maddie. With 2 T's or with 2 D's? Heck yeah. Thank you. And Jared, is that right? All right. 1D? All right, so going back. So any questions on that? I see some people writing fervently. Some English word that's really big that I don't remember. So, all right, so chemical bonding. So we've kind of talked about it with this example. But formation, so basically what a bond is when 2 molecules come together and they bond between the valence electrons of atoms. So we have a few different types of bonds. And he's going to ask you about these types of bonds on a question or on a quiz. I don't know, what was y'all's quiz? What questions were on y'all's quiz today?
He asked a lot of pH.
pH and like bonding, like peptide bonds and stuff like that.
Yeah.
Okay.
He has like the most random questions.
Yeah,
I'm
they
like,
seem very random.
Like, is it hydrogen bonding if it's
some of them were, yeah, like a pH question. Like Ruby. I got both of the which one is a polar or nonpolar. Those ones I got to use on that one. But then I got pH questions too, and I was like looking at it.
talking
and I
about
was
the one with the pH where it is if the pH is going down, you have a net charge of this.
yeah, I got that one.
It's where pH is going down, you have a net positive net charge.
That one I don't.
So he's talking about
It was in the book, but I don't understand.
polarity and pH, and that's probably chapter 2, which we'll probably get to next week. Cool. All right, so first off, the different types of bonds. We have electrovalent, whatever. We'll go through them as we get there. I don't know. Whenever people list them off for me, it's just really hard. I write them on the list, and then you got to write underneath them. And you're like, oh, I didn't make room for that, so we're just going to go through them. So electrovalent, or more commonly, the ionic bond. So the ionic bond is when the valence electrons are transferred from one atom to another. So they're forming the charged atom ions. And that's that example that we just did with the sodium and the chloride, right? Sodium and chloride, where is that found at? NaCl. Where do we think of when we see NaCl? Salt, right? Yeah. So this is salt. This example that we took was salt. Coincidentally, a really good movie. So what it is that this chloride atom is physically taking that sodium atom and incorporating it into its own shell. So we have a negative charge and a positive charge, and then those positives and negatives, like we said, are attracted to each other. So that bond is that attraction between those two positive and negative charges. All right, that's an ionic bond. It's just that attraction between opposites. You could substitute, going back to the periodic table, you could substitute, instead of sodium, you could do lithium and neon, or lithium and argon, or lithium and, oh, I'm sorry, and the one before it, lithium and chloride, lithium and bromide. I mean, it's the same thing. It doesn't matter. For this row, you could just substitute one here, this lithium, and could give it over here to have LiF. I could go into like the ones with like 2, but it won't matter for the test. But it's really just the interaction between the positive and negative. So ionic bonds. Bonds are formed by attraction, a positive and negative charge, and they're weaker than covalent bonds. So we'll talk about that here in a minute. Why? Actually, the why is right here. It's because they dissociate in water, and that kind of comes into the polarity. So the water comes in, and the oxygen has this kind of like partial negative on it, and the hydrogens have a partial positive on it just because of the structure of the way they are. So like those partial positives and partial negatives kind of disrupt the thing that they got going, kind of splits them up, and they start interacting with the water instead of with themselves. And that's why salt dissolves in water, right? You can stir it around and it's gone. You can't see it because those different kind of partial charges on the water is what breaks it apart. Cool. So very weak. Just all it took was water to break it up. And what is our body mostly? Water, right? So these are going to be very fleeting within our bodies. Question, also name.
So the partial
Name, what's your name?
Sarah.
Yes, Sarah.
So partial charges of the water is what's pulling on charges of each, atom individually. So like sodium and chloride.
Mm-hmm.
So the charges are kind of pulling apart,
Mm-hmm.
and that's what dissolves.
Yes.
Okay. Just wanted to clarify.
Yeah.
Is he going to put something like that on the test, though?
No, that's just for your understanding. That's for the fun of teaching it.
Baby steps.
So next we have covalent bonds. I'll give y'all a break here in like 10, 15 minutes so y'all can just get up, walk around. Y'all can only take so much of this stuff. Anyway, so covalent bond are when atoms share valence electrons, right? So so with the ionic bonds, they're very childish. They have not learned how to share. The one just wants everything for themselves. This one, they actually learn how to share. They're becoming very mature. And that's strong, right? We want to reinforce sharing. Anyway, sorry. When atoms share valence electrons, so nonpolar covalent bonds equally share electrons. And you're like, okay, what the hell does nonpolar covalent bond mean? All right, so covalent is just talking about the sharing. And nonpolar. So nonpolar basically means equal. So the examples that are given here are hydrogen and oxygen. So whenever we see oxygen, like in the real world, we're breathing O2 in, right? It's not just hydrogen. It's not just oxygen by itself. It's not one. It's two. And it's not just one hydrogen by itself. It's H2 that's in the environment, right? Well, why do those stick together? Let's see if they draw it. Oh, they have it underneath here. It won't go further. It's going to be a little crooked. It'll be all right. So if you remember on the periodic table, hydrogen only had the one proton and the one electron and the one neutron, right? Well, its valence shell can hold up to 2. That first valence shell the first electron shell can hold 2. So what it does, it says, hey, I only have 1, so I can either lose it and just have 0 electrons, or I could get another hydrogen, and we can share it, and then both can have 2 electrons in our valence shell. So that's why we see things as H2, or we see things as O2, or whatever other example there is because they figured out that, hey, our valence shells are half full, really. They're half full. And if I could just get another one of me, another one similar to me, we can combine and make it entirely full, and we're both really happy because our valence shell is very full. So if your valence shell is full, it doesn't want to react. I'm just kind of backtracking a little bit. If that last shell is full, that molecule is content. It's not looking out. It's not looking to interact with anything because it doesn't need anything. It doesn't need any electrons to make it happy. So when things are not full, when that valence shell is missing some, it says, "Hey, like I need some electrons. So I'm gonna go try to find some." Very reactive. That's why when you have radicals that just have like the one unpaired, like cancer, like when there's radicals in the body, it's constantly looking for places to get it, and that's why cells proliferate. That's kind of off topic, but nonpolar is the equal sharing. So tying it back is when pretty much you're going to see it between two of the same things. Nonpolar because there's not more of a positive charge over here or more of a negative charge over here. It's all pretty equal. If you have two of the same thing, they can't be different from each other. So contrasting that against a polar covalent bond, that's when the electrons are shared unequally. So there's going to be kind of a partial positive and a partial negative within it. So that'll be good right there, hopefully. All right, so we have water. That's like we already said, water is a polar molecule. So this oxygen has it's an electronegative molecule. Whatever, it doesn't matter. It's very negative. It's a very negative atom. But then you have these two hydrogens that are more positive. So if we look at the valence shell, did they draw the valence shell on here? Of course they don't. So going back to the periodic table, we can see that oxygen has 6. Absolutely right. 6 electrons in its valence shell. Why does it have 6? You said that. What's your name? Andrew. Good name. I like that. It's a good, strong name.
So it has 6 valence electrons because it's the 6th row, or like it's just that's what it needs to. I don't know.
It's numbers. Yeah, you're right. You're on the track. Yeah, it's number 6 across, right? 1, 2, 3, 4, 5, 6, right? So with each one across.
The outer shell. There's 2 in the inner shell.
Right.
Mm-hmm.
And then there's 6 valence electrons on the outer shell.
Yes, exactly. So it's going to have 8 total, right? Because it's number 8. So your 8 pretty much tells you how many electrons and protons or neutrons it should have, right? So it's got 8 total, but 6 in that outer valence shell, the one that we care about. So it's got 6. Well, it's linked up with hydrogen, and we already know that hydrogen has 1 electron, right? So it says, hey, okay, I'll take a hydrogen. That'll give me 7. But now it's like, ooh, I really want that last one. I need it. It's like, I need it. And so that's why we have 2 hydrogens. It's water and 2 hydrogens, making it 8 in that oxygen's valence shell. It's happy, right? Water is pretty much it's a very strong molecule found in nature. And so that's how we have this structure is because, so there's a partial negative because oxygen, most of the electrons are over here, right? Most of the electrons, there's 6 that oxygen had. And so they're mostly going to be congregated over here. So if there's more electrons over here, there's more of a negative charge on this side of the molecule, right? So kind of the electrons are being pulled over towards the oxygen. Well, the electrons are being kind of pulled more towards the oxygen. That means the hydrogens, they're going to kind of have a little bit less of those electrons. So they're going to be kind of more positive in nature because all the electrons are kind of being stored closer over here to this bigger oxygen molecule. It's got more. It's got 8 protons, and it's in that middle. It's got 8 protons, so that's 8 positive charges pulling electrons towards it, as opposed to these measly little 1 proton atoms, right? So that pull is so much stronger in oxygen that the electrons kind of just chill out over here. They're more on that side. They're everywhere, but just more often than not over here. So we see this unequal sharing, which is what gives us that polar charge. So a partial negative and a partial positive within the same molecule. Is that good? Okay. Ask questions if it's not good. Those were less sure nods than previous. Thank you.
That's also hydrogen bonding?
No, we're going to get to that next. Hydrogen bonding is kind of similar. You want me to just do it right now off of the water, because water is a really good example.
I mean, if you want to.
Okay, because I think it's next. Yeah, we can do hydrogen next. I saw a half a hand.
Yeah, I have in my notes something that he said was that lone pairs and covalent bonds have an advantage, or they may have an advantage. But I wrote it down, but I didn't understand his reason.
An advantage in bonding. So they are, all right. We'll talk in the break. We'll talk in the break, because
That's what I thought he meant, is that a lone pair, kind of like a hydrogen, would have the advantage because it's just actively seeking another one to make it happen.
Okay, so
That's kind of what the point I got as well.
I wrote down lone pair have advantage to combining.
yeah, it can. So using this amino group right here. So actually, yeah, okay. So this amino group, it has these hydrogens around it, right? So it's got two electrons make a bond, correct? Yes, everyone should say. Everyone, yes, yeah, hell yeah. I have so much power. I'm sorry. So each of these two electrons, these three on the bottom, make one bond. So one bond, one bond, one bond. That's 6 electrons gone. And so there's these 2 left, giving nitrogen 8, making it happy, right? Well, if nitrogen wanted to make another bond, it would use these free electrons to do it, because these are already tied up in bonds with hydrogen. So I think that's what he was talking about, is saying like, hey, if you have these kind of lone pairs all kind of by itself, a bond would happen with that lone pair every time before it happens with these electrons that are already kind of in use and bonded elsewhere.
Okay.
I think that's what he was talking about. So going to hydrogen bonding. That is when a hydrogen atom forms a polar bond with another atom, it takes on a slight positive charge. And you're like, what the heck does that mean? So when the hydrogen atom forms a polar bond with a completely separate atom, it takes on a slightly positive charge. So we're working with 2 different molecules, or 2 different atoms here. We've got the hydrogen bond, or the hydrogen that's over here interacting with another molecule that's over here. And that attraction between the 2, that's our hydrogen bond.
What takes on the slightly positive charge, the hydrogen or the new atom?
Hydrogen. The hydrogen. So, is there a picture on here? Heck yeah. So going to the top of the next page, I'm pretty sure this is hydrogen bonding?
Yes.
Yes. This way.
So water molecule finds another water molecule, making it a hydrogen bond.
Exactly. So a hydrogen bond, there's a couple things that it needs. So it's got to have a hydrogen there, right? So it's got to have a hydrogen. And then what it needs is a highly electronegative molecule. So that's either oxygen, nitrogen, or there's one other one. I want to say maybe sulfur or phosphorus, one of the 2. But it needs a highly electronegative molecule. So water is a great example. Why? Because you've got, we already established that water's polar, right? Who can tell me why water's polar? Anybody? Someone else who hasn't talked yet.
Because it has an uneven charge pooling. There's 2 small positives and a big negative.
Exactly. So the electrons are shared unevenly within the structure, right? And so we've got partial negative over here on the oxygen, partial positive over here on the hydrogen, right? Well, okay, taking that same water molecule over here, there's also a partial negative on this oxygen and a partial positive on these hydrogens. So this partial positive that was created here and this partial negative that was created here, those can interact because opposites, that positive and negative, attract each other. So that's really what it is that it's this hydrogen that's a little bit more positive and this negative that's, I mean, these are tiny, tiny positives and negatives, but those interactions is really an interaction between two molecules based on the different polarities of the molecules. So that's why water is so fluid and strong, is that it can, so like we can pour water and do all these crazy things with it, is because all these different interactions allows it to stay together. That's what keeps water together, is all these different hydrogen bonds, because all these molecules can stay in touch with each other. They can roll over each other. Like this one can roll over and make a hydrogen bond here, and this one can over here, and what have you. That's what makes water so baller, for lack of a really better word. Does that make sense? So the hydrogen bond is not, it's not this bond between the oxygen and the hydrogen of the same molecule. That's a big point to make. It's not this interaction. It's this kind of dotted interaction between two different things, between two different structures. And that's based on the polarities of those things. Yeah? Cool. I'll get up and walk around, get some water. My throat's getting dry.
To learn the functional groups and the amino acids, look those up in maybe the book, like Sarkar's book or something, and like write them down on a note card.
The functional groups of the amino acids. Is this still on? Oh,
Yeah,
oops,
yeah.
awkward. Where did we leave off? Cool. All right, quick review. Who can tell me where proteins are made in the body?
The ribosome.
Yes.
Where?
In the cell, I guess, in the cell.
Okay,
Where,
all right,
yeah,
okay.
let's narrow it down.
Okay,
You were correct, too. All right, what is the process of going from DNA to RNA called?
Translation.
DNA to RNA is transcription. Transcription, yes. Going from RNA to a protein is
Translation.
translation. Yes, yes. So I like to think that before you can, so if you're like learning a language, you have to be able to kind of read it and write it first before you can speak it. So you have to transcribe it. You have to write it down first. And then you can translate it into whatever other language you need to do. So that's how I differentiate. You got to transcribe it first before you can translate it. DNA to RNA, RNA to proteins.
Mind blown.
Cool.
Awesome. Okay.
I'm just gonna pick on what's your name?
Emily?
Emily. What is the difference between a polar bond and an ionic bond?
One of them, they share the electrons,
Mm-hmm.
and an ionic bond, they, like one atom, like, takes all the, like, transfers the electrons.
Yeah, exactly. So the electron is actually physically taken from one atom to another, either stolen or given. I like to think it's kind of like nice, like he like donates it to the other one instead of stealing it, because that's mean. Exactly right. So like it's the electron shifts, and that interaction, the positive and negative charge, is what creates that bond. And with the covalent, they share the electrons. You're right. Emily, is that what you said? What is your name? Eric. What's the difference between a polar and non-polar covalent bond?
Polar is unequal share, and non-polar is equal share.
Can you give me an example of each?
So polar would be water molecule.
Mm-hmm.
So one oxygen takes away the two hydrogen. I'm not equally sharing it.
Mm-hmm.
And then I don't really know an example of a non-polar bond.
The non-polar would be like the O2 or the hydrogens.
Oh yes.
So it's the same thing. So if you ever ask you a test question, what's an example of a non-polar covalent bond? Well, you know it's not going to be water because we've already just I've beaten that into the ground. So you're looking for something that's the same, right? Because there's no way the same thing can share something unequally, right? Because it's the same freaking thing. Exactly right. All right. What is a hydrogen bond? And remind me your name one more time. Nathan. Nathan, what's a hydrogen bond?
Polar bond?
Yeah?
So if there's two negatives and then there's a positive hydrogen, like between oxygen, two negatives, bond in between the hydrogen because the positive's on the other side.
Exactly. So it's you have two molecules that have polar bonds, and the negative from one of the molecules interacts with the positive of one of the other molecules, and that positive is a hydrogen, right? That's where the hydrogen comes into play. So that interaction between two polar molecules, between the hydrogen and the negatively charged one, that interaction is the hydrogen bond. Good, good. Let's move on. Let's learn some more stuff. We got a couple more pages. All right, so water. We're doing water. Special properties. So like I said, it's all about its polarity, right? And hydrogen bonding capabilities. We already discussed this. Boom. I'm so ahead of myself. This is awesome. So water is a solvent, like we said. It dissolves polar compounds. Kind of how it dissolved salt earlier, right? It's very good at dissolving things. So hydrophilic compounds are soluble in water, and hydrophobic compounds are insoluble in water. So hydrophilic, have you all gotten into cell membranes yet in cells and tissues? You all done anything in cells and tissues yet? Okay, so you know how when you're looking at the cell membrane, you've got the that polar head, and you got that hydrophobic tail, whatever, right? So that polar head, it's that same polarity that we've been talking about in the molecules here. You know, it's just the unequal sharing of electrons. So basically, the tails are nonpolar because all it is really it's just carbons and hydrogens. Like, you can't see any of that, sorry. It's just carbons and hydrogens. And they're all like the same, and they're all very happy where they are. So these don't want to interact with anything. These carbon, ooh, hello, what's up? Y'all don't need to see that close at my handwriting. So these nonpolar tails don't interact. There's no polarity with them. So there's nothing to kind of steal, to kind of, not steal, but to hoard electrons in one area as opposed to another. But with these polar heads, you know, there's some negatives over here maybe, and maybe it's a little bit more positive over here, and maybe a little bit more negative over here, so on and so forth. So what it's talking about here is that when you put this in water, this polar head, because there's little negatives over here and positives over here, combined with water that has little negatives over here and positives over here, it's able to dissolve something like this because it's similar, right? So in this instance, when you dissolve something, like dissolves like. And by that sense, like does not dissolve unlike. There's no really better way of saying that, I think. But so if there's a polar, if you dump something that's polar into water, it'll dissolve because it's the same as water. It's a like, so it dissolves like. If you pour something such as just that carbon fatty tail from a cell membrane, it's going to stay that way, right? Best example would be oil on top of water when it rains, right? You can still see that oil on top of it because those are two different things. Water can't dissolve oil because it's hydrophobic. So if it's hydrophilic, it can be dissolved in water. If it's hydrophobic, hydro, water, philic, like enamored with. Like you like it. Not like though, but you just like it. So I'm going to have a lot of stupid jokes. Y'all really just need to bear with me. It helps me. And so that's what it means. So hydrophilic, it likes water. Hydrophobic, it doesn't like water. It's like, get away from me. So that's the basic concept behind those definitions. So hydrophilic compounds are soluble, hydrophobic are not. That might just be an easy test question. Like, do you understand that concept or do you not understand that concept? Effect of extracellular solutes on water movement across the plasma membrane. Osmosis, osmotic pressure. I don't think he's really going to touch on that too much. I don't.
He mentioned it and then just kept going.
That's what I'm talking about.
You went to like the isotonic solution and the hypertonic solution.
Cool. You will definitely need to know those. That's 100% test question is going to be on the test. So the difference between a hypertonic and a hypotonic solution. All right, so hyper. If someone is hyperactive, are they more or less active than normal?
More active.
More, yes. And if someone's hypoactive, are they more sedentary in lifestyle, or are they like a marathon runner?
Sedentary.
Okay, so those are so we already know what those prefixes mean. So tonic is just tone, just like the tone of something. I mean, like a muscle tone. If you have a hypertonic muscle, it's going to be kind of spasming. Just kind of measuring the tone. Like if it's, I don't really know another word for tone. It's kind of awkward, but it's fine. So a hypertonic solution is a solution in which the osmolarity outside of the cell is lower than the cytosol inside the cell. So let's just go and read osmolarity just so we can be familiar with that. That might be the one definition we need to know out of these. So osmolarity, it describes the solute concentration which can exert a specific osmotic pressure on the cellular membrane. So what the heck is that? So who can tell me what the difference between a solute and a solvent is?
A solvent dissolves
Yes.
things, and the solute is the sum of that. What was combined?
Exactly. So your solvent is what you put something in, and the solute is what you put in. If that makes sense. So when we're talking about osmolarity, it describes the solute concentration, so what kind of is put in. This can be anything from calcium or really calcium, sodium, potassium. If y'all remember like how a muscle fires, you have the different calcium concentrations which they build up and then they make everything go, and then then you have sodium rush into the cell and potassium rush out of the cell. Those are solutes. That's what we're talking about. Things that are within a solvent or within, I don't know, I guess the aqueous environment, which can exert a specific osmotic pressure on the cellular membrane. So, example. So if we've got, actually there were pictures on there, that was dumb. They'll have nice pictures. This book isn't actually bad, y'all. I mean, minus all the typos that like destroyed me on the inside. It's not a bad book. So we have a cell in an isotonic solution. What does iso mean? Yeah, the same, neutral, similar. So say you've got this cell that's in a solution, and there's pretty much the same number of these black dots that are inside the cell as there are proportionally outside of it, right? So those solutes are, since they're the same, it's isotonic, right? There's no really movement from the inside of these, from the solutes inside to the outside, because it's the same. They don't need to. It's happy where it's at. Well, say you put in a cell where you put it in a hypotonic solution. So the solution it has less of these solutes in it, right? Sorry, I'm getting confused on myself. Yeah, slow it down. All right, so hypotonic solution, let's just read it first. It says, it is a solution in which the osmolarity outside of the cell is lower than the cytosol of the cell. So for example, the water concentration is higher than the solutes. Okay? So when a cell is put in a hypotonic solution, the water molecules enter the cell and the cell swells. If the entry of water is large and crosses the limits of expansion, the cell membrane the cell will burst. So pretty much cell in hypotonic solution. Okay, I was wondering because this is definitely supposed to say hypertonic. Did y'all get that? Did y'all make that change? And y'all saying, okay, I looked at that and I was like, oh God, it's different than what I'm thinking. Let's go read back and read it so I'm not an idiot. So hypertonic solution. So there's more solutes inside of the cell, and because the cell membrane allows water to pass in and out, right? That's what cell membranes, they make sure that the cytoplasm's in an optimal environment. Well, because there's more solutes in here than there is out here, the water says, oh, I want to balance out. So I'm going to rush inside of that cell to make everything in balance, because that's what the cell is trying to do, is trying to adapt to its environment. And so that cell rushes in. Well, the cell pretty much gets bigger and bigger and bigger, and then like a water balloon, if there's too much water, it's going to burst, right? So hypotonic solution, the cell is going to burst. On the other side of it is a hypertonic solution. So there's too much tone, there's too many solutes outside of the cell, right? And so the cell gets in, and it's like, oh, like I'm doing my thing, but I get dropped in the solution. I'm like, oh, wow, I kind of have too much, the concentration outside of me, it needs more water because it doesn't have there's not enough water in here to match the cell concentration in here. So it says I'm going to get rid of the water, and the cell is going to shrink. So that's why you see it shrinking here and bursting here. Really, what it is, it's the cells adapting to its environment and making changes in water. Because when it comes to osmosis, water is the thing that moves, not the solutes. Kind of fumbled over that a little bit. This one should say hypertonic. So really, test question that he's going to ask is, if a cell is put in a hypertonic solution, what's going to happen?
You know any reason why he wouldn't have told us that in class that it was printed wrong?
You probably just didn't notice it.
Actually, his slides were correct.
Oh, they were?
Right.
Yeah.
Correct. His slides in class were correct, and when I noticed that, I was like,
Yeah.
Started changing shit.
Shoot. Yeah.
Sorry.
No, I don't know. I'm just giving you a hard time. Yeah, so hypertonic solution if that's not in your book. So test question, if a cell is put into a hypotonic solution, it will swell and potentially burst. So really easy, just do you understand it, do you not understand it? Those are the type of questions that students might typically miss just because they're not really quite sure what to study for this first test. But it's really just, do you understand the concept? Can you kind of memorize what is happening in these equations, what the definitions are? All right, so moving on. Acids, bases, pH, and buffers. Heck yeah.
This is where everybody went.
Shoot. I'm just all right, so acids. Acids are compounds that release protons in a solution. So acids are proton donors. All right, so we have acids and bases. So if acids are proton donors, bases are proton acceptors, right? Someone's got to take those protons that acids are just so graciously giving away. And so examples, hydrochloric acid, sulfuric acid, phosphoric acid, carbonic acid, anything that says acid in it, probably going to be an acid, right? You would think. It actually is, so that's good. So bases. Bases are compounds that we just said accept protons or lowers free calcium levels of a solution. So they either, so instead of having the hydrogen floating around, they accept them or they release a hydroxyl group or that OH into solution, right? So everything can be based off water because water can act as both an acid and a base because it has free hydrogen that it can give off, or it can accept a hydrogen, or it can give off that OH group because that's really all it is an H and an OH. So examples, anything that kind of says hydroxide, because hydroxide really is just OH. So sodium hydroxide, NaOH. Calcium hydroxide, CaOH2. Just because ammonium hydroxide, NH4OH. So those those OH groups are bases. So ionization of water, as we can see here, it can be split from H2O into a hydrogen and an OH group. So the ionization water is quantified. So this is where y'all are getting confused is by like the Ks and the what have you, all that stuff, that fun stuff. Heck yeah. So still trying to figure out how exactly to communicate like that part. I've got a decent idea, but it's kind of chemistry background, which is chemistry is the same as biochemistry, just a little bit less life, especially in the teachers too. But whatever. So so what we're looking at is that the K value, which we'll see here in a little bit. So ionization of water is quantified by the ion product of water, and that's a K with a little water. Don't worry about that one. And the base of the pH scale. So the pH scale is determined by the number of hydrogens that are there. So skipping down just a little bit. Like we said, pH describes hydrogen concentration of a solution. So if you have, let's just go down. So pH scale 0 to 14. 0, 14. Stomach. What do we think the pH of the stomach is? What do we commonly hear about?
It's really acidic.
It's really acidic, right? Like people get acid reflux. That stomach acid from their stomach goes into their esophagus. Yeah, good job. Y'all are learning already. Into the esophagus and kind of eroding it, right? So that's got a lot of hydrogens. So that's going to be down here low. So anything from 0 to 7 is an acid. Anything from 7 to 14 is a base. So looking here, HCl is pretty much the strongest acid. It will like destroy your skin. This is why you wear like gloves and goggles and stuff whenever you're in labs, just to make sure that you don't, you can still see the next day if you accidentally spill it. But just looking over here too, like Coke. It says cola, but we're in Texas. Coke that has the same acidity as our stomach acid, and we're putting that into our esophagus, which gets eroded by stomach acid, like we just said, with acid reflux. Think about it. Anyway, so these are our acids, these are our bases, and that says that exact same thing right there. Test question: normal pH range of blood is what? 7.35 to 7.45. So our blood is slightly what? Acidic or basic?
Basic.
Basic. Yes, our blood is basic. Blood basic. But you need to know those numbers. That's the easy test question.
There's also a test question. pH equals negative log pH plus. You said that in class.
Say again?
If you go up a couple to the pH equals negative log, he said that was going to be a test question as well.
pH equals up or down?
Your handwriting.
Where your hand
Oh.
is.
Oh, yeah. Yeah, that'll be on the next page. This is actually a book that I'm borrowing from my friend, so my handwriting is not that neat, as you can tell. But yes, that actually is a test question. I remember that being.
Underneath the K there.
Underneath what?
Right up to your left. Up there.
Product. So K means, I guess he has product K. I didn't write that, so I'm not going to tell you all about it. But we'll find out on the next page what K really stands for. So you won't need to know examples. I just kind of pointed out Coke on there, but you really won't need to know examples of these different ones, so don't worry about like memorizing them. But it is really cool to be able to say, hey, milk is slightly acidic. Human blood, slightly basic. The bleach that you're doing is pretty freaking basic when you're cleaning your stuff, right? So it's going to be a very strong chemical. That bleach is very strong because it's way up here on this pH scale. So that's kind of just more for your own understanding and kind of putting things in relation to each other. But the only one he's going to ask you about is blood, so make sure you know that one. Buffers. Buffers. All right, so who can tell me what a buffer is? Nobody, that's fine too, but someone's got to know. Someone knows.
It's something that balances out the pH.
Yes.
It changes the pH.
Mm-hmm. Did any of y'all take, who here took chemistry in the last 3 years?
Borderline 3 years.
Okay. Or in undergrad? Okay. Okay, who here has not taken chemistry within the last, until you can remember? Okay. Okay. All right, so in undergrad, when I did chemistry lab, don't do chemistry lab, it was awful. But basically, we work with buffers, all right? So what we had like a solution full of our buffer, and we'd slowly drop in like HCl, like hydrochloric acid, right? Super freaking high, very strong acid. Well, we were constantly checking the pH of that solution that we were dripping it into, right? Because we wanted to see kind of at what point that pH would just bottom out and like just drop really low. So, but what the buffer did was it prevented that pH change from happening immediately. So what they do is they, like you said, they kind of balance out solution. It prevents major changes in pH changes, whether up or down, kind of giving your body time to react to different environments. So that's what a buffer is. And we can read the definition here. The pH changes a little when small amounts of strong acid or basis changes, as opposed to a whole freaking lot when a strong acid or strong base is added to it. Yes, name.
Undergrad, Shannon.
Shannon.
In undergrad, I was told, or I think I was told,
Good. That's absolutely right. So what she said is that buffers resist major pH changes when strong acids or strong bases are added to it. Yes? So they resist. That's the way we'll learn how that works out there. But pretty much just knowing that definition of resisting change is what you're really looking for and what it's composed of. So how it does it, it's composed of a weak acid and its conjugate base. And let's see what the next page has for us. Or, there we go, a weak base and its conjugate acid. Y'all want to get into this, or do y'all just want to memorize it? Because I'm pretty sure the only thing he'll ask you is what the definition is and like what it does. So like what it's made up of.
You need to know it for like later on.
I'll tell you in a trimester. I'll tell you when I take boards
Okay.
next try. Yeah, it's really, it's a weak acid and it's a weak base and it's conjugate acid, or it's a weak acid and its conjugate base, and it resists major pH changes. That's really what a buffer is. Yes?
Well, it's written that a weak acid and its conjugate base is more likely found in biochemistry than opposed to a weak base and its conjugate acid.
Good. Add that to the three things. So weak acid, conjugate base, more common.
So the whole thing is a buffer, not like one of the things is a buffer.
So, all right, I guess we're going to go into it. This is awesome. All right, so what happens is you have this weak acid. This one's carbonic acid. I guess we'll go into the example here where it actually says it. So HA, weak acids or bases. So this is just an example. So HA is just your acid that can give off that hydrogen. And it can dissociate into hydrogens and the conjugate base, really, is what that is. So by itself, it's the acid. Then you have the hydrogens and the conjugate base. So because it's given off the hydrogen, it can no longer donate hydrogens, right? So it's no longer an acid. But because, if you just take the hydrogen off and then whatever's left is here could still accept that hydrogen back, in theory, right? Because it's just, all it is just lost that hydrogen. So it's now a base. After it's gotten rid of the hydrogen, it's now a base.
So, is it kind of a neutrality? Like it's.
Explain that further.
Like it tries to neutral it out.
Yeah. Is it so? Shit, I don't know how to.
This is
The acid's turning into a base with the hydrogen.
so.
What is the charge of the hydrogen when it loses that?
Saying here, yeah. This honestly, this is kind of difficult for me to like fully understand because I remember the first like 3 times I learned this in undergrad, it was like over my head a little bit. But he's not going to ask you what an example of a buffer is. He's not going to ask you to like write the equation. This whole test is going to be multiple choice, right? So you have to pick an answer choice, A, B, C, D, or E. So like going through these, thinking of questions that he can ask in a multiple choice setting, he would say, give me an example of, tell me the definition of a buffer. And you'll say it's a weak base and it's conjugate acid, or it's a weak acid, it's conjugate base, and it resists major pH changes. If you know those 3 things, you can easily pick that out and say this is the right answer, because those are the right answers. But he's not going to make you do that equation or label which one the conjugate acid is, I'm pretty sure, so you'll be all right. If he does, then you can come beat me up. I'll ask him. I'll say, hey, what's the most important thing about this? Yeah, I'll email him after this. And I'll be like, hey, what's the most important thing about this? Or we can just do, what's that online? Khan Academy. I'm sure Khan Academy has like a really easy, have y'all heard of Khan Academy? Do y'all know what that is? KhanAcademy.com, I believe. Anyway, type in Khan Academy into Google, and pretty much what it is this professor said, hey, I want to put my lectures online, and kind of similar, and it really just blew up. So they have all different topics from biochemistry to, I used it for physiology. It's a lot of science stuff, a lot of stuff that's really difficult for some people to to talk about. And so if you type in Khan Academy buffer or Khan Academy pH or anything like that, and you can look and see, hey, what do I need to look at? And they'll break it down from the very beginning, and it'll get more complex. So it's a really cool resource if you're looking for something to supplement. I use it a lot for phys that you'll have next trimester. But basic concept of buffers. Good? Speak. Yes, question. Google it right now. Tell me what does it say. I think it's like the reciprocal or opposite. Yeah. Well,
That's the word that's been throwing me off too. Is like that's specific.
Talk about when you say conjugating. Give the different forms of as they vary according to voice need, chance number, and person.
Go to biology.
yeah, type it the biology one.
Become temporarily united in order to exchange genetic material.
Type in the chemistry one.
So we'll never have to like identify which one's the acid and which one's like conjugate base, or what's the conjugate acid is going to be weak base, because that's kind of where I get confused is knowing which one. I mean, besides the one that has the hydrogen ion, like knowing which one is the conjugate base and which one is like the acid.
Yeah, but I can't apply that equation.
Yeah.
Figure it out.
You got to visualize it. I'll try to find a good link and send it to you, because whatever I'm going to say right now is not going to do y'all justice. This is like the one. I mean, we all have weak areas, but this is one of the ones that I need more practice with, to be honest with y'all, and I don't want to confuse y'all further, tell y'all the wrong thing. But you get it? What is it?
No, I looked at like 5 different websites to find one that actually freaking makes sense. So it says in chemistry, a conjugate refers to a compound formed by the joining of 2 or more chemical compounds, or the term conjugate refers to an acid and base that differ from each other by a proton. By 1 proton, says the proton.
So the conjugate is the acid minus this electron. So that's why you have like the conjugate. So you have the weak acid and its conjugate base, because it's lost the acid, versus if you have the weak base and the conjugate acid, the conjugate acid has gained that electron.
So it's just calling it base just because it's just a little bit more basic than what it just was.
Bingo. See, like y'all are tutors, y'all should do it. Y'all should do this.
That being said, can you
Joking.
kind of help me understand, like, when he's like, oh, these are important buffer systems, hemoglobin buffer, bicarbonate buffer, phosphate buffer, what do they do? And this is like physiology, like, what do they do?
So the buffer system's really, give me an example. Just pick one of those that you just said.
Hemoglobin buffer.
Hemoglobin buffer. All right, so what does hemoglobin do? It carries the oxygen, right? So say you are, say you're sprinting, right? So, or say you're hyperventilating. You're hyperventilating. So you're taking in all this oxygen, right? But you're not expelling any CO2. So that hemoglobin buffer system allows your body kind of time to adapt before you faint, right? So you're hyperventilating, you're going, you can do it for a while because you have that hemoglobin in your system to kind of offset those like major pH changes. But at a certain point, it exceeds that capability, and then you wake up 20 minutes later. So that's what, yeah. So then you have like the phosphate one or the other system is the same thing. Just it's resisting major changes that are happening to your body that could be detrimental, and allowing you to rectify it hopefully before something bad happens.
But wouldn't that be saying, like, for hemoglobin buffer, it's a good thing for you, because if you went out for a run, sure, you'd be on the ground, right? Because your body cannot buffer that change, right?
Yeah, pretty much. It's helpful. A little louder. A little louder. Do you want the mic, or you want to be louder?
I'm good.
Good.
So I said that I think it's mainly for when you have like your labs and you're running tests and you're trying to separate things or combine things. That's mainly how it's applied.
Know the buffer systems. Know the different types of buffer systems. He might ask you like which ones they are.
The teacher referred to it as like a bumper car.
Okay.
Ooh.
It seems like a bad one, but you're just like kind of takes a lot.
Yeah. Let that one settle in for a little bit. Well, maybe we'll start with that next
I
time.
use the term all the time, buffer. Like, yeah, time buffer. Like, some.
I mean, like if you're out,
That you kind of like put in place just so.
yeah. I mean, like
Safeguard.
if you're out and you're at the bar and you know someone is hitting on you, right? Well, you put your friend in the middle to buffer you from the weirdo, right? To protect you. It's a protective mechanism. Or like you'll throw your friend in the middle of a dog attacking you, so you're like, I'm good, and thanks, you saved me. I don't know if you're a bad friend. Anyway, other questions? Good? Can we move on? Well, let's move on. All right, so Henderson, Hasselbalch, let's go stay right here. So for a weak acid, the weak acid, HA is weak acid, or just acid in general, because it has a hydrogen. Dissociation constant is determined by the expression, this thing right here. So dissociation constant, if you can see, that's a Ka. I forget what the A stands for exactly, but the K is like your constant, even though it's a K. Yes.
Is the A be the conjugate base for acid? It's just like whichever conjugate it is.
That might be right. That might be right. But the main thing is the K. The Ka is equal to the products over the reactants. So if you look at this, I'm on the wrong one. So it's been dissociated. What's dissociated is on the top. So the final product is on the top. And the starting materials, that acid that has not been dissociated yet, is on the bottom. So that's really what the H and the A and the HA stand for. It's the hydrogens, the conjugate base, and that's that acid. And so dividing those, so multiplying those concentrations, those bars, those brackets just mean concentrations. Multiplying those and then dividing it give you that number. Knowing that equation, he's just going to ask you equations. So that's the Henderson-Hasselbalch equation. Test question.
Product over what?
It's products over reactants, or the final product over your starting materials, whichever way that resonates with you best. But if I remember what he did a year ago, he just said, which of the following is the Henderson-Hasselbalch equation, or this is an example, like what is this equation called? And you just had to be able to regurgitate that memorization info. We can derive it.
What is the Henderson-Hasselbalch equation?
It's the same thing.
Then what's the one directly underneath where your hands were?
Oh, shoot. Oops. Yep, you're right. Jumped ahead. So it's derived from this. So you're right. Good job. So it was derived from this, and it will be, so sorry. Derived from equation, or pH. It is this one. The pH equals pKa plus log AHA. So I'm just going to tell you to memorize that. I'm sorry, I'm going to tell you all to memorize that, but we got some other stuff that we need to cover. So this right here. Test question, what's the Henderson-Hasselbalch equation? Not that. It's derived from this. It's that one. And so what it is, it relates pH. So we've been talking about for the last however much pH. So kind of the concentrations of hydrogens in the solution with that pK, the concentrate, oh my God, pKa. There's so much like BS chemistry that's like in this sentence right now. And the concentration of the buffer, and like that buffer here. We're not going to go over. We'll go over pKa here in a second, but just memorize it. Just memorize. It'll be fine. You'll be fine. Yeah. So important buffer systems. Boom. We talked about that. And carbon has a unique role in biochemistry. So we're kind of switching topics here a little bit. Actually, that's, yes, functional groups, and then we're done with chapter 1. So I'm going to try to do a chapter each time. Should take like 2 hours. He does it. I don't know how long he takes, but I think breaking it down like this is nice. Chapter a week. So carbon has a unique role in biochemistry. All biomolecules are carbon-based. So other important molecules, elements are hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And that's what makes up kind of the organic part. Those are like the organic atoms, organic elements. Important metal ions. I don't think he'll ask a test question about what the important ones of those are, but those are listed. But there's 30 other elements that are essential for life. That's why we have a whole periodic table, because they're found in nature and they help us stay alive. So, carbon. This is just, all this is pretend. So you know how earlier we had oxygen and we had lines to hydrogens, like those lines were bonds? That's all these are. So all these lines are just bonds connecting atoms. You could draw H's here. This is just the shorthand. Or you could draw really another carbon right here or what have you. H's would just make it easier. But this is just a shorthand. It's not naked. There's stuff on the other side. It's just imaginary. I don't know why he would throw that in there just like that to confuse you. But really this is just saying carbons link with each other. We talked about the fatty acid tail, right? It was just hydrocarbons, right? It's just that carbon tail. That's all it is. Carbon's very versatile. Going on to the next part, it can make a lot of different bonds. You know, it can bond with hydrogens. It can form 2 bonds with nitrogen. It can bond to oxygen. It can bond with itself. It can double bond with oxygen. You know, it's just saying that it's pretty much a lot of the structures in our body in some form or fashion have carbon in it. That's why we have classes like, organic chemistry, why we have inorganic chemistry, which is, I think inorganic chemistry is only carbon bonding. Like they have like 3 classes of that. So it's very important, and it's also found in biochemistry, obviously, too. So the functional groups are biochemical reactions involve the functional groups. Biochemical reactions involve functional groups of molecules. So we can say that functional groups are kind of like, what's an example here? So like when you're playing different sports, you have certain things that you use to play that sport, right? So say you're playing baseball. You have a baseball bat, helmet, glove, cleats, pants, whatever. You know, like those are the things that are necessary. Those are kind of like the different tools to like make those happen, right? And those are like the identifiers of that sport that you're playing, right? So if you're playing football, you're not going to have a baseball, right? So each of those things has its own function that's particular to what it's used for, right? And so that's similar to what it is too. Like these are kind of identifying groups that are found on molecules that are important for carrying out functions of life. And that each of them do something different, because if the same thing there's like billions of reactions happening in my body right now. And you can't have just the same molecule doing all those different things, right? We have different necessities within the body. So we have different functional groups performing different actions within our body. So this is just really, the next part is just learning what these different functional groups are and really just their names. Not really going to talk about the function of them. It's just really just memorizing the name. Because I don't need to teach you how to, It's just very, very surface level. The names can be kind of difficult though, so I would definitely. Okay. So.
That means rest of the equation, right? Or rest of the formula.
Yes. So an R group, as we'll find out in for the amino acids next week, an R group is pretty much just carbon. That's it. It's really, it doesn't matter. It's either something that we're not concerning ourselves with, we're just not concerning ourselves with. What's highlighted from here on out are the things that we're focusing on. So really, the equation starts from here, and that R group is meant just to make sure that that carbon has a full valence shell, because each bond is 2 molecules, right? So 2, 4, 6, 8 carbon is happy, right? Because how many electrons are in carbon's valence shell? 8, yeah, 8. So that's kind of, it's like a placeholder to make this equation equal up. Does that answer the question? Cool. Almost done, y'all. Almost done. 2 more pages. All right, so these functional groups here. Methyl, ethyl, phenyl. So methyl, when we're learning, like methyl and ethyl are kind of just the most basic carbon structures that we have. So methyl is just carbon with 3 hydrogens, and ethyl is 2 carbons. Don't even worry about the hydrogens. It's 1 carbon and hydrogens, and ethyl is 2 carbons and hydrogens. All right, so it's similar like mono. Like mono means 1. Same thing with methyl. Methyl, mono, 1. Ethyl, the only way I know how to do this is to tell you how I finally remember this in my own chemistry class. So, all right. So we said, no, that's diethyl ether. We'll get there later. Ethyl is 2. Those are the only 2 that you need to know in numbers of carbons. Phenyl is, it's a ring. So it's, or phenyl, whichever way you say it, I don't know. But basically it's just a ring structure that is all connected, and there's 6 carbons within it. That's what a phenyl is. It's going to be kind of boring. I'm sorry. Try to have a bad joke or 2 or 1,000 for y'all. That's fair.
Really, I had 2 questions, and they mine 2 of them. It was like, what are these? Like, what is this?
Did you say I answered your question, or you have questions?
No, that was like these are important. You said it's boring, but it's on the quiz for today. So.
Yes, yes. So just learning, just familiarizing yourself with them. There'll be kind of like a practical application here at the end, the last structure that he has. Carbonyl groups. Carbonyl, whichever one. So I don't really, that's sliding off. That's kind of cool. I'll walk with it. So we have 2 different carbonyl groups. I never call them by that word. I usually use aldehyde or ketone, and I'm pretty sure he will too. So you have your aldehyde. Remember, everything that we're talking about here is the highlighted thing. The other ones really don't matter. They're just placeholders. So the highlighted group, the aldehyde, is it has this C double bond O with an H on the end. So carbonyl is talking about this carbon-oxygen double bond. That's what that means. So the carbon, and I guess the nyl is going to be the oxygen part of it. So you have the aldehyde. Aldehyde has the H in it, so that's COH. Your ketone is like the O is in the middle, so that's all it really is you have just the C double bond O. And so where these are found, so aldehydes, since it ends in H only has those 2 electrons that it can kind of combine with, right? Well, both of those are wrapped up in this bond with carbon. So really, this is the end of the molecule. This is the period. This is the end of that sentence. Well, the carbonyl, the ketone, it doesn't have that H. It's just the C double bond O by itself. So really, it can be found in the middle of molecules, or it can really be found anywhere. But the difference is the aldehyde has the H, ketone does not. It's just the C double bond O. That's the only main difference. All right, ether time. Heck yeah. So ether. I learned it as diethyl ether. Who can tell me what ethyl is? 2 methyls put together, or a 2 carbon molecule, pretty much, right? It's the same thing. Same thing. A methyl plus a methyl equals an ethyl, because there's 2 carbons something that has 2 carbons in it. So how I learned it was diethyl ether. So what the book says is, what did the book say? I lost the page. He has it as ROR, right? ROR. So I'm just going to make it a little bit more applicable. The main part here is this O linkage. The ether is just this O that's kind of put in the middle of other crap next to it. It's not crap, it's important. But anyway, so how I remember this is that diethyl ether, right? Because this is a C right here and a C right here. It's really shorthand. I apologize, but those are 2 C's. So these are 2 ethyl groups. 1, 2. Oh, God. Heck yeah. All right, so these are 2 ethyl groups, right? Because this is just C with H's around it. I'm drawing a little shorthand for you, but so this is pretty much, instead of this hydrogen over here, it's just attached to that O. Now you can see it, sorry. All right, so ethyl, and then we have this diethyl ether, and it looks like a bat. So an ether group, or the diethyl ether, has this O bat looking thing on it because it's that O linkage. So that's just how I remembered it. So ether is that O, and I draw a bat. I had to draw kind of a more complex one. I mean, I could just write R's on here, like an R group, but you remember a bat easier than you will an R group. Yes? No? Maybe? Hopefully? We'll pray about it later. All right. Next, we have ester. But before we start with ester, we're going to do a carboxylic acid. All right. We only have carboxylate on here. So we have carboxylate, but we're going to pretend this is carboxylate, but we're going to pretend that it says carboxylic acid for right now, right? So a carboxylic acid is COOH is a carboxylic acid because it has that H on it, right? So it has an OH, so it's got to be an acid. That H is still attached. Well, it's called carboxylate when it loses the hydrogen on the end. So whenever you see something with the suffix ate, it's going to be something that's got an O minus on it because it's lost that hydrogen. So ate is kind of just a suffix for something with an oxygen with a negative charge on it. If you put that hydrogen back on, you get carboxylic acid. Take it off, carboxylate. Put it back on, carboxylic acid. Okay? So, cool. So that's carboxylate. So pretend this is carboxylic acid again, right? So we have COOH. Going up to this ester here, I don't know why I'm putting it so high. It was fine. Probably because it's slipping. It's the same thing, COO, but instead of that H, it's an R group. So there's more than just the H there. So these two are super similar. It just depends on what's coming after that second O. All right, so carboxylic acid is COOH. An ester, different from an ether, which is higher up. I can actually reach that now. Different from an ether, an ester is COO with an R group after it. All right, we're getting blank faces. Almost done. I'll get y'all out of here. Questions? Concerns? Still waiting on some compliments. All right, so we have an acetyl group, and we have 3 left. So let's just do the more important one that you'll see more often. Let's start off with what we all like is alcohol, right? Alcohol. It's one of the easiest ones. It's just an OH group. That's it. If you see OH by itself, it's alcohol. But if you see, I kind of wanted to draw on that, but that's probably not very good. But if you have this COO in front of it, it's a carboxylic acid. So that's the only difference between a hydroxyl, is if you put a COO right there, COOH, you'll get that. But the OH by itself is your alcohol or your hydroxyl group. That's probably one that he'd probably pick just because it's not too bad for the test. And enol, so en and all. The all, we kind of see anything that ends in the suffix ol, like an alcohol, is going to have that hydroxyl group on it. It's going to be an alcohol, right? So this enol, that ol, shows you that it has an OH group on it, right? And chemistry is going to tell you everything you need to know about that structure, which is really nice. If you can just learn the language, you'll be just fine. But you got to transcribe it first before you translate it. Sorry, I'm terrible. All right, so we have an ene, and there's 3 different types of bonds. This is going a little bit extra, but ooh, that's terrible. All right, so we have an alkane, an alkene, an alkene. You'll need to be able to read this, and an alkyne. All right, so this is a single bond between carbons. An alkane is. An alkene is a double bond between carbons. And an alkyne is, you guessed it, a triple bond between carbons. All right? You don't need to know these terms. But for an enol, I just wanted to show you that there's, for the alkene, this is the one that I was trying to point out, is that there's these 2 bonds between carbons. That ene, right? That ene. So when you have the enol, you have that double bond between carbons. So you have both the ene for the double bond and the ol for the alcohol on the molecule. So just look for those things. If that's the one he picks on the test, just look for those functional groups within that one molecule, and you're good to go. And your acetyl group, that shouldn't be a double bond. If y'all have that should be a single bond. Basically, it's your ketone just plus a methyl group. I don't think he'll pick that one. That's my guess. But an acetyl group, there's really nothing really too special about this, but it's just you have that C double bond O with a methyl group after it. Acetyl group. All right. Moving down.
Oxygen significant?
No, it's not highlighted, so don't worry about it. Functional groups. All right, so now we've got. Oh, where'd that do? What did that do? Okay. We have our amino and amido. These are going to be important to know. We're learning our amino acids, right? Not our amido acids. So amino, this is a protonated one. So just you can either pretend that this is the R group is here, or you can just pretend that those are lone pairs and there's no charge. I could explain that. It's not worth it. So amino group is NH3. And amido is NH2 with the C double bond O on it.
Can those also be referred to primary amine and secondary amine?
Probably.